Yeah.
Yeah.
So Paxos is like a consensus protocol, and the consensus is a process of agreeing one result among a group of participants. Say these are the group of participants, right? So everybody can send one value. So this is a proposed value, and by using Paxos or consensus algorithm, we could choose one value among all these things. And we'll talk about Paxos here, how it is consensus achieved. Um, so Paxos is invented by the Lamport in the late 1980s, and Paxos is used in Chubby, Zookeeper, Google Spanner, Megastore, and there are many more. And for the log replication, how the Paxos is used, so that we will explain. So I have a slides for that. Let me maximize the slides. So these slides, I mean, there's a Diego Ongaro. So this guy presented these slides, and then I mean, I referred many documents, but I did not get clear idea. But after going to this videos and presentation, I got better understanding of Paxos. And I thought of making slides, but there's more or less same with my slides also. So I use this one. So I don't see any issue, right? If you share somebody else's session.
No, it's fine. I mean, it's in
Fine.
the public domain. So, yeah.
Okay, fine. So now for the replication log, right? How Paxos uses like I'm not able to show the cursor here. Okay, let me maximize this. Are you guys able to see it fully now?
Yeah, I think I'm fine. Like if others have any issue, please.
Yeah, fine. Okay. So we have client machines, and these are the servers. Say we have like in the clusters like 3 or 5 servers. And then each server will be having a consensus module. Say in this case, Paxos we are talking about, and it has a state machine, and then the log. So now for this consensus algorithm, the log will be appended to this log. I mean, whatever the new command comes from the client, that forward to the consensus module. Now consensus module will transfer the same command to the other followers in that. And then once it gets the consensus from them, then it appends to the log. Once it gets the majority of the servers, if they're okay to agree on the value, then it appends to the log. And from the log, the sequentially it applies the log to the state machine. So now state machine, why we talk about like so here state machine is like when we give input, so we have multiple machines here, right? So all the machines have state machine. If you give the input in an ordered fashion, then it gets the same output. Say if one machine crashes, right? Still, with this state machine, if you give the ordered input in any of the machine, the output will be same. Okay. So the system will be available as long as a majority of the servers are up. Say you have 3 servers, right? We need at least two to operate actually. If you have 5 servers in the cluster, we need at least 3 servers to be up and running, so that the consensus module will be available and we can use it.
So we follow quorum or what, or it's simply
Yes.
like 3 or
yeah, we follow quorum of like majority. So it's not a quorum, we call it like a say out of 5, right? What is the majority would be 3, right? Yeah, it's called a quorum.
more than half plus 1.
Yeah, more than half plus 1.
Question.
Yeah.
So is this Paxos is in context of multi-leader, leaderless, or anywhere where we need consensus?
So this consensus would be master slave architecture, I think, because I have seen somewhere like we could use multi-leader as well. But what my understanding is like you could use master slave architecture. Say for suppose you have Hadoop, right? HDFS, there is a master node. So that's a single point of failure. Okay, instead of HDFS, we can take a Zookeeper. So zookeeper will be like zookeeper is a master slave architecture, right? So in that, now zookeeper, like to make it high available, we can maintain one master and multiple slaves. If any one node crashes, one of the follower will become a master, and then he will continue to serve the cluster.
So is zookeeper single master or multi-master?
A single master zookeeper.
Okay, so I was wondering that I thought in single master, whatever master says, slaves just follow. Like basically, they are followers, right?
Right.
So I don't know. I'm not able to understand where this consensus is coming in picture here. Consensus would be in probably, even in a normal life context, you will ask from suggestions or agreement from people who are at par, right? Like if there are 4 admins to a system or 4 masters in a system, then you would want them to say, okay, we all agree on this value. But if there is just one master, and I'm a follower, I'm just going to agree on what the master says. If the master says the value of A is 1, I'm just going to follow that.
Yes,
But if there is a part
yeah, I mean, you are right to answer
election.
that, right? Say for
But I
example,
think-
the master is crashed, right? I'm sorry, someone is speaking.
No, I was saying that if there is a network partition between master and follower, then also in that case, in single master and follower, if there is a network partition, right, still you need a consensus.
No, follower doesn't take rights, right? So what consensus do you need on?
But in that case, your follower won't be updated to that of a master, right? Because earlier there was a connection, so they were passing the updated information.
Yeah, so
to the
follower will
and
just copy the write ahead log from the master, and that's it. There is no kind of I don't think there is kind of an agreement that master is waiting from a follower.
But
No,
so you're saying that there's one master, right? So for other followers, how do they know that who is a master? Say all of a sudden master got crashed.
Okay,
Now
so the
who will
consensus
become-
is about election of a master. Here are
Yes,
we talking?
consensus
Okay.
also election will come into. Yes, so for the election also we use.
I thought it was about the data. Okay.
No, data also we use actually. Consensus.
Okay.
Because say one leader is there, okay, he told some set of commands to execute to store in the log, and all of a sudden he didn't get all the response from the followers and he crashed. Now the new leader came, and now he doesn't know from which state he has to follow. So whatever previously the leaders is sent the law send the new commands, those are partially accepted by the some of the followers. So when the new follower become master, it has to know, right, where to start from, and how to make the consensus of the log among all the followers and himself. So I mean, these all things, I think once you go to the slide set, you will understand all like
Okay,
step by step.
sure.
Okay. But as you mentioned, like I mean, this multi-master, right? So we explain here multi-master point of view first to understand clearly. Then we'll go to master slave. So Paxos, right? They say like the Paxos suggests that use one leader and then the follower to get the high efficiency and high availability. But it can still support if there is a more than one master, one leader. It works actually. Okay, we'll see that in the slides. So Paxos, right? It is very difficult to understand actually when you directly go to this multi-Paxos, and multi-Paxos will be used in the production. I mean, to understand that, we decompose into two set of problems. One is basic Paxos, and the other one is multi-Paxos. So for the basic Paxos, so we have set of servers. Okay, so in that we have two phases actually. Each server can act as a proposer, and then it can same way act as an acceptor also. So for the basic Paxos, we have like they call it single degree. Say so basic Paxos, right? We agree on one value on a particular index, and for the multi Paxos, we use a multiple instance of basic Paxos to achieve the multi Paxos. Okay, we'll just go through it one by one how it implementation wise. So for the basic Paxos, they say safety, only one value will be chosen finally. And whatever the value chosen, every server will get to know that which is the value it got chosen by all. And there's a liveness. So as long majority of the servers are up, then majority servers should be up always. And then what is the proposed value? One of them sends, that value will be eventually will be understood by all the servers. So for the Paxos, there are two components. One is proposers, second is acceptors. So for the proposers, it will take the client request actually, and this is the active component. So it will choose a value and then sends all the followers to accept the value. So now for this proposer, it get a votes actually from the acceptors. If it gets the majority of the votes, then that value will be chosen for the particular index. Any questions until here? And here each Paxos server acts as both the components actually. It has to contain both the components for the basic Paxos. Okay.
Is this Paxos is like a, sorry, go ahead, Shisha.
Well, on previous slide, there was like state of the decision we store it, right? So what is that? I mean, store chosen value and state of the decision process.
Which slide you're talking about?
Previous.
Here?
No, I mean, go ahead. Forward, you have to again. Yeah, third point. No. Third point in the acceptors.
Third point is in acceptors. Okay. Store chosen value and state of the decision process.
So, why do we need to store the decision process, right? Already we have a mutual, I mean, a value is there where every node has, has a consensus over it, right? What is the state of the decision process?
State of the decision, store chosen value and state of the decision. So here maybe I understand like so it will give us a value, and then the so actors, so for the acceptors, right? So until the whoever proposes, right, he will say this is the value you need to accept. But end of the day, for accept, it will not be knowing that value is really chosen. So for that chosen value, it has to maintain the state, I think. But anyway, we'll just go through further slides and maybe we'll get better understanding on that.
Okay. Yeah, that's good.
Yeah, I had a question about Paxos, which says each Paxos server contains both components. So,
right.
Is this a Paxos server is a part of my pod in a microservice architecture? Like, or it's on my application server as a part of application server? How does this kind of deployed?
Oh, okay. So as I mentioned earlier, right? So for the Paxos, so there's a leader-based Paxos only we use. I mean, then the multi-Paxos, right? For the understanding, we will be explaining about the single Paxos. There everybody can and send as a proposals. But whereas in the end production side, we use multi-packs. So there's one leader will be there, everybody else will be followers. But the thing is, well, deployment, we use multi-packs. So am I able to answer your question?
Yeah, sure. A little bit, maybe it will get clear. Yeah, sure.
Yeah.
You can move.
Sridhar, one question. How would application know like who is the leader? Is there any proxy layer or like application will contact directly?
So yeah, that's a good question. So generally, this Paxos will be used internally by the zookeeper. Say, so now zookeeper will be knowing who is the master. Okay, so and then if an application trying to connect, right? Say for suppose zookeeper used by Hadoop, right? If you say Hadoop, HDFS, right? So the followers has to know who is the master. So at that time, So in the zookeeper, there's a tree hierarchy they maintain. So in that, they say who is the master actually. When the server and the followers trying to join the cluster, so they will check in the path who is the master. From that, they will understand that.
Okay. Yeah. Thank you.
Paxos doesn't have the concept of master.
I'm sorry, somebody speaking.
Paxos doesn't have the concept of master, right?
Your voice is not audible.
Paxos doesn't have the concept of master, right?
Paxos internally has, right? It has a master slave architecture.
Okay, I thought Raft has Paxos is lead. Okay.
I mean, one guy will be leader and everybody else will be followers for the multi-Paxos.
Okay, the proposer you are treating it as master.
Yes, yes.
Okay.
Yeah. So this slide I think is not needed. Let's go to the next one. Say now acceptors, right, will send the values. Say now we have 5 servers, S1, S2, S3, S4, S5. So now in the single degree Paxos, each server will accept as will have both the components I mentioned, right? It can oppose a value and it can accept someone else's value also. So now S1 sends one value actually. It sends as a send this value, is right? And now S3 also sends blue and S5 also sends green. Say now each acceptor accepts only one value. So does it come to a consensus? Say now server 1 as broadcaster saying, hey, I'm trying to propose a value, right? It got accepted by S1 and S2. Now S3 is trying to send a value as blue. It is accepted by S3 and S4 because now how S2 is already accepted another value is a red color, and now S3 sends blue, it will not accept because the condition we mentioned, one server accept only one value. So if you do this way, right, the votes will get split and we don't get any majority for any of the value, and finally we will not choose any value actually. Okay, so for this the solution is, so what is the solution for this? So each server can accept multiple values.
So basically, if one server accepts one type of value, it can't accept other type of value. Like
Yeah,
since it
yeah.
has accept.
Yes, I mean this is a condition I mentioned at the starting, right? I mean here, if you see in this slide, acceptor accepts only one value. It got it.
First it receives.
Yeah. For the first iteration, whatever it gets, that value it accepted, and second proposer trying to send a new value, the server will not accept that one. So if you do this way, the votes will get splitted and will not get the consensus. End of the day, we don't choose any of these values. Any one. Our aim is to choose one of the value, right? Out of this, the one value is to choose any.
Yeah.
So now, because we have 5 servers, right? If one guy is saying that, please choose blue, so he should get majority of the votes. 3 guys has to accept that. So now 3 guys has sent 3 different values, and then it got accepted by 2, 2, and 1. So we didn't get majority, and then the value will not be chosen. So then we'll go another round of iteration again. Okay, for this the solution is the acceptor can accept multiple values, right? Say for suppose now S2 accepted is a head, right? Now S3 sent a blue. If this guy accepting blue also, then you will get the majority, right, of S3. Now blue is chosen between S2, S3, S4. So in the second iteration, we can transfer the same blue value to the S1, S4. All will be in the consensus, and the blue value is finally chosen between among all.
Sorry, I didn't get it. If acceptors can accept multiple values, then again we can be in a state where there is no consensus because everyone has accepted all the values.
Yeah, there's a problem. Yes, I'll come to that. Say now everybody accepting the all values, right? Say now S1 send this one, it's red. it got accepted by S1, S2, S3. And now this red is chosen because the majority it got, right? Say now S5 came all of a sudden, and so it says, hey, please accept blue. Now blue also got accepted by S3. Now S3 is chosen both the values. So now there's a problem, right? Now because of S3, it is accepted the previous value and the new value. Now blue is also chosen now. So there's no guarantee here, right? So we don't have any consensus here now. Because of S3, it accepted red, and now it's accepting blue. So there's a problem. So here the solution could be when S5 trying to transfer blue, right? When it proposes blue, it has to learn if any value is already accepted. Say now so from at this point you can able to understand, right, whether in this system, if other servers the other servers accept any value. So that time it can choose that value, and he can transfer that value actually. Is that clear?
No, the last part wasn't clear.
Okay. I have a slide for that. I'll show you that. So here what I'm saying is, once the value is chosen, the future proposals must choose the same value. So now for S5, when it's trying to propose a blue, it has to understand what is the value it got accepted already. Instead of blue, it has to take the accepted value, and that value it has to propose.
But it didn't get red at that time, right? I mean, S1 sent the red and it was accepted by S1, S2, S3. So
no, I understand. No, so red, from what I
Oh.
understand, the red is already accepted.
It's
And
already accepted, right?
Yeah.
Because out of 5 servers, 3 servers already
so S5 before proposing has to read the latest accepted value.
correct.
Okay. So
But
Mhm.
what if red is not the majority? Let's say S1 sent and red was accepted by only S1 and S2. Right.
Oh, okay. At that time, the value is not accepted actually. So it can
Okay.
send the blue at that time. I mean, there are further slides.
Mm,
Whatever questions you ask it to valid, we have slides for further on those.
Okay, till the point it's not majority, it will not be accepted, right?
Yes,
It will keep on. It can.
Yes.
Okay. Mhm. Yeah.
So they call it a two-phase. So they call two-phase protocol here. Say one server trying to propose a value. First, prior to that, it has to understand what is the accepted value. That is phase 1. And the phase 2, it can choose the same value and then send the accept to every server. Okay, so here there's one more problem. So in the two-phase also, the problem is now, say now server 1 sent one value, it got accepted only by server 1, and it went very late to the server 2 and 3. And prior to that, now server 5, it chose a blue, and it got accepted by S3, S4, and S5. Now blue is chosen. But whatever the request earlier is sent by S1, right, that went late actually. So that value also, I mean, now we are not sure whether to choose in the previous value or the new value, right? So this problem could be solved by using ordering actually. So we can order this request, the first proposer, when they send it, by using the sequence number. So the older sequence number we can abort, and the newer sequence number we can make them wait.
I have like doubt here, like already red is occurring 3 times, right? So that's a majority value. So why?
But the thing is, 1 second, for the server 5, right, when they're trying to transfer blue, at that time this value is not accepted actually. It got by only one server 1 only, because at this point in time when he's trying to understand what is the accepted value, he don't get any accepted value at this point of time. So it sent blue only.
No, but before that, red is accepted by 3 of the servers, right?
Yes.
S1, S2, and S3.
Earlier,
So it's already a majority.
no, here, right, in the earlier slide, when S5 trying to send a blue value, at that time, this previous file is already accepted, right? At this point of time, this is the time. If you can consider the timestamp here, at this time, it will talk to all others servers. Right? So now it got reply saying that S1, S2, S3 got accepted this value. Right. But here, is it fine, clear?
Who generates those numbers?
Hello?
Who generates those numbers for ordering?
Yeah, that will explain in further slides. Yeah. So, so this slide is clear, right? Any questions?
No, but here also the value which is proposed by S5 is after S1 only, right? Before that only S1 has distributed this red to S1, S2.
Correct, correct. So, okay, at this point of time, now S5 will talk to all the servers saying, hey, have you guys accepted any value? So it got only one response from S1 saying this got accepted. But here we don't have any hazardity, right? So earlier we got 3 responses actually from S1, S2, S3. But here we got only one response.
Okay.
Okay. So now, this one, okay. So here the solution is older unaccepted proposed values could be dropped actually. So to drop that, we need to maintain some ordering of the events. So there is a sequence number we can attach to the each of the proposer. So when the server trying to propose a new value, the older proposals like incomplete ones will get dropped actually. So there's an algorithm for that. Then further slides is there. First, we'll try to understand all the scenarios. What are the scenarios? We'll see the issues. Then later, when you see the algorithm, it will be clear. Okay. For the sequence number, as I mentioned, right, how it is generated is there is one number. It is shared among all the servers. That number sequence will get incremented every time when we're trying to propose a new value. Plus, there's a server ID because we need to understand from his proposal came from which server, right? For that. So this is the number each server will be having. Now let's see how this one will happen. Okay. So for the basic Paxos, we have a two-phase approach I mentioned, right? We'll broadcast the prepare RPC. And here we'll try to find out first if any value is chosen. And then the older proposals will get dropped. And then the chosen value will be sent in the accept RPC. So there are two phases. Okay, now let's go to the algorithm, how it is done.
Question about this, these steps. If we go back into the diagram where we saw the problem. So here, yeah. So I mean, it said that block anything older. So
Right.
how would S5 know anything older exists before when S5 is proposing? Since it's not yet accepted, how does S5 know if there's anything older being proposed by anything else?
Okay, that's a good question. So now S5 will not be knowing actually. So he will broadcast, right? So that
So who will block?
S1. I'm sorry?
Who will block?
Yeah. Now it goes to S1. Now S1 will get blocked actually. He will not further continue transmitting his value. Is right.
Who will block it? S1 will block itself?
Yes. He will block
because
himself.
he will see an accepted value for a particular key. Okay.
Right.
Okay.
But S1 has the sequence number, right? It knows that it sent already. So why would it block? It's just that the sequence, it's not reaching S2 and S3 because of time network delays. But S1 knows that the sequence by sequence number, it has pushed those reds earlier than S5, who's proposing.
But higher are given priority.
Because here
right?
mentioned it, higher order proposal will get win actually. Finally.
Okay, higher order. Okay.
Yeah, higher order will get win.
chosen is different from accepted. Accepted doesn't mean it's chosen. Chosen means it's the value has been has reached that consensus stage. So,
No,
so
chosen.
when
Yes, you're right. The chosen is like once the consensus is done, then the chosen will come into picture. Now we are trying to say accept this value. So it could be it could be accepted or not based on the consensus.
yeah,
I mean,
so when
we have an
so
algorithm.
whenever
Then we'll get clarified all these
Yeah.
questions. Okay. So each scenario, right? I'll show you the algorithm. From that, I'll point out in which step this will get blocked or it will get invalidated. Okay. Okay. So here, okay, these two steps is very important to understand the algorithm. So here we have like two RPCs we use in the basic Paxos. One is prepare, another one is accept. For the prepare phase, the server will be having its own value to propose. But prior to that, it has to find out if any value is already chosen among the servers. So if it's already chosen, right, it has to drop his own value and it has to pick the chosen value. And if any older proposals are ongoing and the value is not chosen for them, those should be blocked. We should block them. I think it's fine, right? Are you able to understand?
Chosen and accepted are same. Yeah.
Would you repeat that?
Chosen and accepted are same. Do they mean the same thing?
No, chosen is like there is a consensus in the module, so that value is chosen.
What is accepted?
Okay, we say accept. It's not accepted. We say accept means we are trying to tell them that accept this value. They may accept or they may not.
Okay, but in previous diagrams they were accepted. So this chosen and accepted are same, right?
Oh yeah, choose and accept is same. Yes, in that way it is same. Yeah, you're right.
So,
Okay,
sorry.
okay.
Oh, okay. 1 second. I think it's not same.
It's not same. It's just
yeah, because
kind of an
choosing is
acknowledgement from one instance
one
that it has
instance, right?
accepted.
You're right.
Got it.
Hey, while you were here, I had one more question. If the proposal from Blue, which is S5, it is delayed on S1, and by the time S1 has already pushed those 3 reds, still you will end up at a state where you have S2 as red, S1 as red, and you have 2 values on S3. Is my understanding correct?
I think you're talking about the scenario, right?
Indeed. Yeah, that is possible, right? S3 has
Yes.
Okay, got it.
Yeah. So here in this slide, we have all the scenarios we have covered actually, like all possible ways. There are like some more scenarios are there. I'm going to explain after this one algorithm. Okay, so these two steps are clear. We should be clear. If you don't understand these two steps, then the algorithm will not be clear. So there are 2 phases. One is prepare phase and accept phase. So in the prepare phase, whoever is trying to send a value, they have one value. Okay, to understand this, say for suppose we have an array index 0. Okay, for the array index 0, we're trying to the server trying to send a value 1 into it. Instead of say x. So in the index 0, it's trying to propose a value x. Okay, say for the 0th index, someone else has already chosen the value y. Okay, so if already someone is chosen value y, instead of x, you take y only. And then there are some other proposals. They're trying to propose g, but that is still ongoing. It's not succeeded. So those proposals will block it, and the value is already chosen y, right? And we'll take the y and we'll send the y as accept to all the followers. Okay, I mean all the acceptors. So if no value is chosen, whatever value we're trying to choose x, right? That value is sent to all the acceptors. Is that clear?
Isn't it based on ordering, like whichever higher number got? It does not I mean, it doesn't matter whether it is chosen or not. If one comes with a higher number, I'm going to choose that. Isn't that the whole point?
If there's no accepted value, then we'll choose that. Yeah. So prior to that, if someone value is already chosen, right, then that time the new one will pick the whatever value chosen, right, that value. Okay, we'll go to this this algorithm, then we'll get all the things clear. Say now one server is trying to propose a value x. I don't know how to write it here, but I'm not able to write here. Okay, let me say one server.
You
is
can
trying to.
annotate.
Yeah, you can annotate me. Switch on the annotate.
Oh, annotate.
Yeah.
Where it is? Oh yeah, annotate.
I'm also not getting
You're also not
that
getting
option. Is
fine, but anyway, I'll just put it over here only. So now server one, right, is trying to propose a value. Server one trying to propose a value x. Okay. Now, as I mentioned earlier, like it has to choose a number, the sequence number actually. So the sequence number consists of one number plus the server ID. Okay. So it chooses the number n. Okay, to all the servers. Now it broadcasts to all the servers. Okay. So this prepare goes to all the acceptors. Say now other acceptors, once it get this prepare, it internally compares if it's already accepted any proposal. So I mentioned that if a higher order proposals will get stored here. Whatever the new proposal I got, if that is higher number, that proposal will get stored in the acceptor. Okay. So from this, I can tell the older proposals will get dropped. I mean that step comes in step number 6, but I'm just giving a hint here. And if that.
what is the value of minimum proposal initially? Like you are comparing now, if n is
The
greater than
minimum
minimum.
proposal initially you could assume as 0 because here the server number starts with 1, right? I mean it's up to you. Like we can assume the minimum proposal number. You can make it assume it as a 0.
Okay.
Because we are already comparing the max one, right? Which are the max one, that value will store it here. You see this if condition. Say earlier, right? The min proposal is 1, you can assume. Okay. Now this prepare phase we sent 1. So we sent 2. Now 2 is greater than 1. Now the min proposal equal to 2, right? So what are the previous transactions happening to 1? Those will get dropped.
True. Yeah.
Okay. So now and the so whoever got this prepare, right? Those acceptors, if they already accepted some value for that index, they will send the accepted proposal and then accepted value. So accepted proposal means the same thing. Yeah, the whatever number we have sent, right? The previously, if it is accepted something, that number and the value, it will just give it to the server one. So now he will, once he get the majority, right? Majority from the followers, then it compares, then it picks the majority accepted value.
So one quick question, the step number 3, it's always, the acceptor always responds to the proposer, is it? Whether it accepts the
always,
incoming number or not. Okay.
Right. So if it has an accepted proposal and accepted value, yes, it will send it. Okay. So now it got it actually. Okay. Now the proposal, as I mentioned it in this phase, it has to block the older proposals, and then if any chosen value is there, that value it has to choose. So now as I mentioned, right, now it's trying to propose value x, but prior to that it has to understand if any value chooses. Say at this time, let me do like this, maybe x comma or 2, and the 2 is like n actually. Let me write here, this n equal to 2. So now this accepted proposal, right? Say for suppose it got accepted. Let me write it here. The accepted value is y, and then this accepted proposal number is 1 actually. So now it got accepted proposal number 1, and then the actual value is y. So if it got majority, right, then so whichever the highest proposal number, that number it will just take it. Say like now I accept 1 cents, the number is 1 and y, and then I accept number 2 cents, the proposal number 2 and then value g. So then that time the highest number will win. So that value will just take internally, and then that particular value, now here n equal to 2, right? And the value, say for suppose y is the max highest you can assume until now. So now it choose the value y, and this value, say it will ask other followers to accept this value. And then for other followers which gets acceptors, the value, the number and then the value, it compares internally. So here, right, at this point of time, as like earlier, the step number 3, the min proposal we made is like so here n equal to 2, right? So if any so for the previous proposals which is smaller than 2, those will get dropped here, will not process them. And then the which is higher one, so that value will compare. First of all, 2, right? 2 is greater than or equal to min, it's true. Now it will accept the value as y here. Is it clear now? Now the y will be sent to the 6 now. The 6th step, once it say like what are the values accept, it sent back to here. And here the server S1 heads from the measure to the servers. So if this number is greater than n means someone else got win. You did not win. Now we'll go back to step number 1 again to choose the new value. The value, whatever value we are trying to choose x size. Now it goes to index number 1.
So in 6th step, it should be strictly greater, right? Why that equality is there in 6th respond to the accept? I mean, there is a function here where you are passing 2 parameter, right? N comma value. Acceptor side.
Right. Here
it will be equal, right?
So
Greater than equal to is right one.
Why so?
Yeah,
okay, that's accepted value.
So here, right? I mean, I got the same question. It should be equal, but the thing is, yeah, even I'm also not sure. Yeah, it should be equal, but
Also in item number 4, I think it says if any accepted value returned, replace value with accepted value. I think it should also say with highest accepted value for highest accepted proposal. What if different accepted values are returned for a given highest accepted proposal? Like in your case, the highest accepted proposal was 2. Let's say, but one of the guys returned accepted value y, another guy returned maybe accepted value a, or maybe it's not possible. I don't know. I was just trying to think.
So here, right? So say for suppose multiple followers are sending multiple accepted proposal numbers, then in that we will take the highest number.
No, I'm saying within a given highest accepted proposal number. So let's say you have 2 of them returned accepted proposal 1, 2 of them returned accepted proposal 2, 2 of them returned accepted proposal 3. So let's take the case of 3. Now 2 of them returned accepted proposal as 3, but within that, if the accepted value, I'm thinking, could it be different? I mean, if it's different, then condition number 4 should be changed to replace value with highest accepted value.
I think that will not happen, right?
Oh, is it? Yeah, maybe.
Because the value will be same actually. If the
Okay.
sequence number is same, the value should be same.
Yeah, let's go with that to keep it simple. I mean, as it is, this is complicated. Let me not make it more complicated.
Yeah, there are like some more scenarios if you go. I mean, okay. Is it like some level is clear, or you want me to explain from the beginning again? Maybe I'll just go back 1 step back. So here, right, for the prepare phase, we're trying to find if any value is chosen, and you block the older proposals, right? So that step, if you come here, so here we are trying to learn if any value is chosen. So that value will get here in this step, and the older proposals will just overwrite actually. So here only new proposals will get processed. Older ones will get dropped here because there is step number 3. in the step number 6 here, it depends on the step number 3, because the min proposal will just overwrite, right? The old one will get dropped. And if any accepted value is there, that accepted value will send to the proposers, and this guy will be, we will pick that value, and it will just send it to the all the followers in the accept. Say if there is no accepted value, and whatever the if there's no accepted value here, right? If it's not sending any accepted value, step number 3. At step number 4, it will pick his own value as X, and that value it will just broadcast to every followers to accept it. And then how do you get to know whether your value is really accepted or not? So that is a step number 6. Once it sends the min proposals, right? So if it is greater than your number, then it's definitely that your proposal value is not accepted. So if it is equal, then the value is chosen, then you're done. If someone else has got chosen, then again you go back to step number 1 and start the same procedure again to accept your value.
So
do
my
I-
question is, this on the left hand side, which you're saying proposers, is it only one proposer or more than one proposer at the same time?
Same time, multiple servers can send multiple values.
So, I mean, who initiates this? So we are trying to find a leader here or a value.
Oh, okay. So here there's no leader. All are like all can propose a value. Here actually, say you have a cluster of 5 servers. Now 5 servers will accept the client request at the same time. Same time, in the sense more or less same time. Say there are 5 servers and 5 clients. They're trying to send 5 values to 5 servers, and they're trying to they're trying to propose all the values. And at the end, we need to choose one value, right? So that how is assured that they're trying to prove here from this algorithm.
So each
Generally-
acceptor at the same time, he's also, in addition to responding to prepare, potentially is also sending a prepare to.
Yes. So the point I mentioned, right? Each server will act as both proposer and acceptor.
Wow.
I have a question. I'm on the 6th point. Maybe we can make it a 7th point on the proposal side. So it says if any rejections result is greater than n, go to first. And the first one you choose new proposal number n. So for example, I have been trying to propose a value, say x, for my key k1, and it gets rejected, right? So again, I will increase my number and say, okay, again, for key 1, I want to propose X. I should accept the new value, right? Why would I go on and propose a new one if I know there has been a higher order value that has been accepted by others?
Okay, you're saying if it's already accepted, then why you're trying to
Create a new
propose
proposal
a-
number and just, beating around the same bush when I know it will be rejected. Like,
okay, I got your point. Yeah. Okay, I'll tell you that. Yeah, that's a good question. So
So
here,
let me get this question. Let me get this question correct. What she is asking is, let's say we this guy proposer sent n equal to 1, but already things have moved on to n equal to 2 for the rest of the machines, and they've agreed on some number, some accepted number. Then the question is, why is this first proposer now going to n equal to 3 or something?
The proposal number might increase, but the value is the same, right? I'm trying to again propose the same value with a new proposal number. Like so that's, I don't think is the right way, because that value is already updated after me and everyone has accepted. So I should accept and like move on, right?
Okay.
Yeah, you're right. So the thing is here, right? So okay. So now there's index, right? Say for suppose one array is there. For the 0th index, we are trying to compete actually, and then you lost for the 0th index. Someone else's value got accepted it. Now you compete for the index number 1. Try to store your value at index number 1. So for that, you'll go to step number 1.
I think what is not clear is what is Paxos trying to achieve? Are we trying to achieve a consensus, or are we fighting for a resource? What are we trying here?
I mean, say for suppose for one resource, we are trying to compete, right, between multiple servers. So whoever trying to all the servers will finally agree to one value to be chosen for that index. Say for
So
suppose
is it a storage consensus? What we are gonna store at what resource?
I mean the
Or for
log
what
replication,
keyword we
right?
are gonna store?
I mean, this is for log replication, right? If you see the slide number 1 here, see the 0th index. So this log indexing, right? The log array. The first index got accepted with the add command. The second index jump. Third index for move. So this, if you see all the logs, right? The log replication means the replication should be same among all the servers. So the client one, you're trying to say client one send one. Okay, not client. Say server one is trying to propose add to the index number 0, but server 2 trying to trying to add jump to the index number 0, and server 3 trying to add move to the index number 0. So among all, add got succeeded. It's stored at 0th index. Now the jump, the server 2 trying to compute, trying to propose
Okay,
jump.
okay.
So that will be stored in the second index, right? So the algorithm has to go on, right? So one index is already chosen by somebody. Then we try to compete for the second index, and then we try to and based on the consensus, if you win it, you will get your choice to save the value over there.
Okay, got it.
Is it clear now?
Yes, yeah, thank you.
Yeah. Okay, good. Let's go to next. Okay, there are some scenarios how this algorithm works, right? Say now server 1 is trying, I mean the same thing what I explained earlier, right? We'll just see from the diagrams. Now server 1 is trying to choose value x, and then it proposed a value x for x with server the number 3, the sequence number, and then the server ID 1. That value went to all the 3 servers, S1, S2, S3, and all are accepted actually. S3 accepted, S2 accepted, and S1 also accepted for value x. Now server 5 is trying to propose value y. So when it sends this propose, right, as I mentioned, at this time we need to get if any already accepted value. So there's an accepted value x, right? So that value it will choose x instead of y. Now server 5 will pick the x. With that value, it will send accept to other followers, say like S3, S4, S5, other acceptors. So here, I mean, in this prepare phase, it got to know about the value x is chosen, and further it drops its value and it's chosen the x, and that value is sent as accept to everybody else. Now there's one more example. Say for suppose now it proposed a value, and then only one guy accepted it, like S3 only. Okay, S3 accepted. When S5 trying to propose the value, it saw the value actually at S3, saying the value is already accepted. I'm sorry, earlier I mentioned that the majority, right? Here I think the majority of acceptors only it has to know. There's no in that it can pick the which are the accepted value. So now this x is accepted one server. That value the server 5 can pick it and it can transfer it in the accept phase. Is it clear?
Yeah. So here the 3 means 3.1 means accepted proposal dot accepted value. What does 3.1 mean?
Oh, okay. So the 3 is sequence number. 3.1 is like sequence number actually. The 3 is for this sequence is incremented among all. This value is shared among all the servers. And then .1 is like server number, whoever trying to send. Because now server 5, right, trying to send a new proposal, it has to increment from 3 to 4.
Okay, thank you.
Dot his own ID. That's to put.
So your server 2 could have also sent, I mean, instead of server 1, no, and that value could have been accepted by all the S1, S2, and S3.
What do you mean server 2 can send?
I mean, S1 is proposing the value, right?
Right.
And that is accepted by S1, S2 and 3. So same way S2 can also propose the value and it could have been accepted by all the three, then it will be 3.2, 3.2, no? Or is it mandatory the first server only has?
Oh, okay. You're saying that so for every new proposals, the number should not be same, it has to increment. If some other server like S2 trying to propose a new value, that has to be like 5.1, 5.2. If it's doing somewhere out here at this time, 5.2.
True,
Okay.
yeah.
So here, say now S1 has proposed a value, but nobody's accepted here. I mean, there's only one server accepted, but when S5 trying to propose value y, it did not see this value because now it got for S5 trying to send the propose, it got accept only from the S3, S4, S5 because this value is not replicated at S3. I mean, not accepted S3. So it will choose y only here. So that y will get accepted at S3, S4, and S5. And later point of time when S3 comes here, this will get dropped here because the higher sequence number will win, right? You remember in the algorithm, the higher sequence number will always win.
But actually 3 is accepted, right, already. I mean,
Correct,
S1
but 3 is accepted at the only server 1. But the thing is, you will not wait for all accepted to reply, right? So it got majority from S3 and S4. This is the algorithm here. It got the majority, right? It will not wait for all. Let me show you that. See here.
no, like
it goes from
in
the
this
majority, and in the majority, if there's no accepted value, then it will choose his own value as accepted, and that value will try to broadcast.
Yeah, but in that diagram, S1 proposed a value, right, 3, and it was accepted by S1, S2, and S3. I mean, the diagram which was this one. So S1 proposed the value 3, and it was accepted by all the servers, S1,
Right.
S2, and S3, right?
Right.
So now when S5 proposes, that won't be accepted, right? X will be accepted only because that okay, that acknowledgement is being sent. Yeah.
Yes, you are right. Now at this point of time, when S5 trying to propose a value y, it only saw that x is accepted, so that it choose an x only here.
Makes sense, yes.
And
so in the next diagram, it's not accepted by the other two, right? That's why
it's not accepted by other two. But the thing is, at this point of time, it saw from one of the servers is accepted at S3, so that value it picks up and it trying to broadcast again in the accept. It will drop his own.
So question here is, we only see these 3 every time. So is there some configuration that says we only propose to 3 because that will give us the majority?
No, this is
a
number actually. These are okay. You're talking about this 3 is every time shown.
No, S1, S2, S3 is what S1 is trying to propose to, and then S5 is trying to propose to 3, 4, and 5. Right? So is there some value like Paxos says that this is what between
that is what we talked initially, I think n by 2 plus 1, more than half of the servers plus 1, if that is the majority value will be accepted by everybody. More than, I mean,
no, I think that picture can be a little confusing. That 3 boxes PPP doesn't mean that S1 is sending only to S2 and S3. S1, S2, S3 all are sending prepare at the same time.
Oh, no. Now S1 is sending prepare, and that got that message went to S2 and S3.
Yeah, so her question was every time, why is it that whatever comes from S1 goes only to an S2 and S3? Why not to S4 and S5?
No, not that. My question is only to 3. Not, it can be any 3, but it will be only to 3.
It could be any 3. I mean, to explain simpler, right? They just picture this diagram like when
True, but it will be 3. That's what we have kind of somewhere configured, that we are just gonna propose to 3 and try to get a consensus.
No, what do you mean by 2, 3?
Oh, really? I thought it would be to everybody, right? Why would it be?
No, I did not understand. What is this 2, 3?
2, 3 is like 5 by 2 is what? 2 plus 1, 3, right? So 3 is
okay. You're talking about majority. Okay, one question.
That is what I think she's asking. Yeah.
Okay, now S1 trying to send the prepare, right? The prepare goes to every server. Okay, but there, if it
Okay.
goes to every server, right? If every server is accepting, then at that time there is no point in proposing a new value, right, for y, for s5. No,
Okay,
we
so
are talking about a
we
scenario.
broadcast to every server. Okay.
Yeah, it broadcast to every server. But we are talking about a scenario where it went to 3 servers, and the server 4, server 5, they didn't know about a value is accepted, or the new, or the proposal came from another server. At that time, they are trying to prepare a new, they're trying to propose a new value. What is the behavior that they're trying to explain?
Okay. But we only
but-
expect an acceptance from n by 2 plus 1 to call it a consensus, right?
Right. If once you get majority, then we say the value chosen. Okay.
From n by 2 plus 1 to the end. Yeah.
Is it clear
Yeah.
now?
Yes.
Okay. Now let's go back here. Okay. So here, as I mentioned, when S1 is trying to broadcast a propose, it went to all, but yeah, it went to all, but only 3. I mean, one of the 3. I mean, 3 out of 5 send got the prepare, and then the S1 accepted 3.1, and when S5 trying to propose Y, and it did not see any accepted value because somehow it did not get any reply from S1. It got response from S3, S4, S5. It got majority. So at that time, it will conclude that there's no value chosen, even though it is chosen at S1, but it did not get any. It did not get any prepare accept from S1, so it will not see the value, right? At that time, it will go ahead with its own value Y. So that value will say accept at S3, S4, S5. When at that time, once this got accepted, so in between, if it gets 3.1, it will drop it, because the step number 3 you just saw, right? Min proposal. So the in proposal, the condition will get failed here because you're already accepted 4.5, but 3.1 is smaller than that. It will get dropped. Is that clear?
Yeah, it's I think a little confusion is we are saying accepted, and that is very server specific. So a server can reject a value seeing a higher order value that it has already received, but that might not ultimately be the chosen value, right?
You're right.
But
You're
it will get corrected in the following steps.
the following steps. Yes.
Yeah. Okay.
Okay, there's one more point here. I think you brought up the point, right? Now, how do this S1, S2 will get to know about 4.5 and Y? So now it has to propose again, actually, this S1, S2. At that time, it will update the accepted value here.
Correct. Yeah.
Got it? Yeah. Nice. Okay. So here also there are some problems. There's a live log will happen actually. Say now S1 trying to propose 0.1, and then prior to accept phase, there is one more server S5 can propose a value. It was trying to propose. Now at the time of S3, it already accepted 3.5, right? Now 3.1 will get dropped here. Okay. Okay. Now. Okay. For server 1, its request got dropped. Now it will try to propose again with 4.1. Okay. When it's trying to propose with 4.1 for at the time of S3 server 3, because it already accepted 3.5 earlier, now we got 4.1 higher term. Now we'll drop the 3.5. So in this way, if you do right, we will not get any consensus here, because each one is trying to compete with each other, and then we are not getting majority, and the value will not be chosen at the end of the day. So
Yeah,
for this,
everybody will come.
Hello.
No, I'm saying every other server will come with a bigger number, and
Yeah,
other
bigger
will
number,
cancel it.
and then will get dropped. Already will not get any majority. So the solution what they're suggesting is this Lamport. So for this prepare phase, right? Instead, don't try immediately. Take a random time delay. Okay. So then if you do that, then this scenario will not happen, right?
Come again. I couldn't get.
Just a minute, do my slides and stuff. Okay. So now what is happening is, if you see this one, right, it's trying to propose a value, and then prior to accepting it, someone else is propose a new value with higher order term. So the previous proposal will get dropped. Now he is trying to propose again a new value. So this is getting interference with the older proposal. Like this we do it. So instead of proposing immediately, so for the server S1, if you could wait for some time with some time, right? So this scenario will not happen, right? So now it is trying to, so once this accept is failing, it is trying to propose a new value immediately. So what Lamport is saying, don't try immediately, take some delay of some randomized delay at each server. So that time this sequence of events of proposing will not happen. So this problem will not even, this problem will get solved in that way he's saying. Is it clear?
Yes.
So what will happen with delay? So that, I mean, like, so others can propose the value in the meanwhile, right?
Oh, yeah. Meantime, someone else can win, right? So if you are trying to propose every time without even waiting for delay, then it could happen that all are trying to propose a value, and chance of occurring this interference will happen, right? Then nobody will win. If you add some delay, means this proposal may not come over here. It may fall after this accept phase. So the server file will win meantime. Okay.
So, but every
Okay,
server, when it is proposing, should it not be should it not have a randomized delay every time?
Yes, they will have. I mean, if they have that, then this problem will not happen, he's saying. If they don't have, then that time this problem will occur.
Yeah, because everyone starts doing at the same time, which is likely to happen. So for that reason, it has to be randomized always, right? Yeah.
Yes, it has to be randomized always. You're right. Yeah. That is always.
So how much will that delay? I mean, random delay, like.
Yeah, that may be based on the history data, everything, right?
Based on the number of servers, and then how much time will take to process the each phase. So based on that, you can choose the time in between.
You could also try exponential backup.
Oh, yeah, exponential backup.
Exponential backup might delay the consensus, right?
Yeah,
And
But you will achieve.
And our eventual consistency will probably be greater. So
Yeah, here the random value we don't. I mean, so if you don't know the random values, we could actually start with one value and we will eventually end up with that value. Here we are not talking about the liveness time, right?
sorry, I didn't get that.
I mean, I'm just saying that select a random value, but you might not have history or these times, right? I mean, if that random duration of where you are picking that value, if that is small, you will again end up with these things. But if you are going with an exponential delay, you will be, I mean, since the delay is exponentially increasing, at one value you would definitely end up with that accept the chosen value. I mean, I'm saying consensus will be achieved. I mean, it might be delayed, but it will be achieved. I'm trying to say that.
Okay, you're saying exponential backup per server, not like for every server there will be. Okay.
Yeah, for every server, not just one server, right? No, I think
no, like if one server gets a reject for a proposal, right? Then I think what he's saying is then we can do exponential backup. Then
right,
the next try
right.
would be in a later time, and at some point it will get accepted. Yeah.
I mean, they do it 2 times, like one at the time of start. Okay, everybody, when they're trying to propose a value, they can do a random delay and then they can start. And again at the fail time also. when it
But
gets
my
it's not
question-
accepted.
But my question here is then, for example, if we do this exponential back of what I saw is we are trying to create this log, right? Ultimately come up with a log that everyone agrees to. This should be the sequence of whatever actions that are happening on the system, right? That's our
Mhm.
log. So if we do exponential back off, then that action that should have taken place earlier, because some client requested it at say time t1. Now with exponential back off, we are probably be able to accommodate it at time t6. Will it not impact the ultimately what we are gonna see, like the value, the result of our row or the state of our database?
Okay, your question is not clear to me, but so the thing is, right, the thing is, if no server is doing any progress, then ultimately there's no server, no client's request will be served, right? So we are saying try to serve one request at least. Then for the second request, the one will succeed, then other one will get chance, right, to serve. So for one request itself, we are trying in a loop like this, and we are not achieving any consensus for the client request. The client request will get delayed, right?
No, I agree we should have randomized delay. What I had a question was particularly about the exponential back off. That will that impact the state of the system?
Okay.
Yeah.
Okay, I think we are not expert in that area, right? But anyway, I think that question we can skip, I feel, because we'll just stick with the delay itself here, because there's many important to talk about the Paxos. Maybe we'll take that as separate session.
Yes, sure.
That's fine, yeah. Okay, so here, right, for the multi-Paxos, okay, the problem here is seen like in the basic Paxo, what they did is every server will act as a proposer and acceptor it. If you do that, right, we are seeing a lot of conflicts actually. So these conflicts, if it happen in the real time, right, will not be able to serve any client request. So in the multi-Paxos, what they did is they went to a leader election actually. So only one server will be the leader and everybody else will be the follower. So the proposals will come from the only one server. It will not come from the all servers. So the problem is solved in the multi-Paxos. I mean, his problem will not happen in the multi-Paxos because only one server will trying to will send the proposals. Okay, here once the okay, this we already spoke about these points. Okay, for the multi-Paxos, okay, we'll continue or we'll stop it here because we crossed more than an hour, because we finished the basic Paxos, and then for multi-Paxos maybe we could take another session, I think.
Yeah, let's park it over here. I think we have crossed more than an hour.
Yeah, more than an hour. And then multi-Paxos is like more important than the basic Paxos. Here they have introduced many advanced things, because so in the single Paxo, right, there are many loops actually. So that how they optimize in the multi-Paxos, that they explain here. So this is more interesting. Maybe we'll take a separate session actually for this multi-Paxos.
Sure, Monday we can have it.
Yeah.
And there is this, Nick is asking if if there is only one leader, why they are talking about multi-Paxos?
Okay. So the thing is, the multi-Paxos means so in the single Paxo, right, we are trying to get the consensus for only one index, one value. Whereas multi-Paxos, they say like for the multiple indexes, how the request will be served parallelly. So in single Paxos, right, a single Paxo, what we will try to serve only one client actually as a whole. Whereas in multi-Paxo, we'll take multiple values from the multiple clients, and then how do we achieve the consensus among all the values? That's what these are multi-Paxos.
Okay.
Yeah, it's something complex and advanced. Yeah.
Yeah.
No problem. Yeah. Thanks, Sri. Yeah. Thank you very much.
Yeah, and then